but it's found in 90% of all known compounds. Carbon is one of the most remarkable of the elements. Most often in nature, it is combined in the air as carbon dioxide, in rocks as carbonates, in the cellulose of plants, in fuels, and in foods. Carbon is part of man-made plastics and synthetic fabrics. Living matter itself is a complex mixture of carbon compounds. Carbon is also remarkable because of the different forms in which it exists as an element. Diamond, the hardest substance found in nature, is one form of carbon. Graphite, the so-called lead in pencils, one of the softest materials found in nature, is another form of carbon. What explains why carbon exists in such different forms? Carbon is element number 6 in the periodic table. Let's think of the carbon atom in terms of an atomic orbital model. The carbon nucleus is surrounded with 6 electrons in different energy levels, or orbitals. 2 are in the 1s orbital, 2 are in the 2s orbital, and the others are in 2 of the 2p orbitals. This ground, or lowest energy state of the carbon atom, can be diagrammed like this. The arrows represent direction of spin of the electrons in each of the orbitals. The empty box represents a 2p orbital not occupied in the ground state. When energy is added to the atom, it will shift from the ground state into an excited state. One of the 2s electrons moves into a 2p orbital. A redistribution of orbitals called hybridization then results in their having the same energy. This hybrid is called sp3. Now there are 4 unpaired electrons instead of 2. In this state, 4 additional electrons can be added from other atoms to form covalent bonds with the carbon atom. The bonds result from the pairing of electron spins. In this excited state, the orbitals take positions that are the maximum distance apart, since the electrons repel each other. Geometrically, this means the orbitals are directed toward the corners of a regular tetrahedron. In the formation of diamond crystals, all 4 hybridized orbitals are occupied. This model shows that each carbon atom is covalently bonded to 4 other carbon atoms in what is called sp3 bonding. This arrangement takes the shape of a tetrahedron. Each of these atoms is, in turn, bonded to 4 carbon atoms, creating an interlocked structure in 3 dimensions. The numerous sp3 bonds make diamond the hardest substance known. Graphite, which is also pure carbon, has different properties because all the hybridized orbitals are not always used. In crystals of graphite, each carbon atom is bonded to only 3 other carbon atoms in what is called sp2 hybridization or bonding. This creates a linear array of atoms forming a layered molecule with each layer loosely bound to the others. This loose bonding explains why solid graphite is easily cleaved into sheets. Graphite is among the softest materials known. It was recently discovered that when graphite is subjected to high temperature at very low pressure, small transparent crystals called white carbon are formed. The white appearance is caused by light being scattered from the many surfaces of the crystals. Under high temperature at tremendous pressure, loosely bonded carbon atoms in graphite rearrange to the structure of diamond, with the numerous interlocking bonds that impart to diamond its extreme hardness. So differences in molecular structure account for the different forms in which the element carbon exists. What explains the very large number and variety of its compounds? We saw before that the carbon nucleus, with its 4 electrons in the hybridized orbitals of the excited state, can become surrounded by 8 electrons. When the 4 additional electron waves are supplied by hydrogen atoms, the compound formed is methane, CH4, and the structure remains tetrahedral. But all carbon-containing molecules do not have this shape. The shape depends on the number of atoms bonded to the carbon atom. In this scale model of carbon disulfide, you can see the molecule represents a linear array of atoms. If only one atom is bonded to carbon, as in carbon monoxide, only a linear arrangement is possible. Molecules of carbon dioxide are collinear. The carbon tetrachloride molecule takes the tetrahedral shape, as does the molecule of the compound methane. When 4 atoms bond with a carbon atom, this is the molecular geometry observed. Methane makes up about 90% of natural gas used for cooking and heating. Methane is the simplest of a vast number of compounds called hydrocarbons. These compounds are formed of just the 2 elements, hydrogen and carbon. A wide variety of hydrocarbons exists because of certain unique bonding characteristics of the carbon atom. We saw that in the methane molecule, a carbon atom bonds covalently with 4 hydrogen atoms. But carbon atoms can bond with other carbon atoms just as readily. When a carbon atom bonds to another carbon atom, 1, 2, or 3 of the 4 hybridized orbitals can be involved in these bonds. In chemical reactions, these bonds may break apart. Then atoms other than hydrogen, such as bromine, can be added, leaving a single bond between the carbon atoms and forming a substitution product. In some hydrocarbons with multiple bonds, one of the covalent bonds breaks, and then, in a chemical reaction, the molecule joins with other similar molecules to form long chain compounds called polymers. In polymers, such as polyethylene, there are many repeating molecular units. Polyethylene is a plastic with many uses. Because of the arrangement of the hybridized orbitals, carbon atoms can also form rings as well as chains. This is the scale model of a molecule of benzene, the best known of the ring compounds of carbon. Benzene is used as a solvent and is the basis for a whole group of derivative compounds. Many chemicals, especially dyes, drugs, and explosives, are made from ring compounds. Rings may be single, as in benzene, or multiple, as in the naphthalene molecule. Although the molecular formula of naphthalene shows the number of atoms in the molecule, for hydrocarbon molecules, structural formulas are more commonly used. This is because different arrangements of the same atoms can exist. What does this second bonding characteristic of carbon result in? This molecular composition can be represented by 2 different structural formulas. Each represents a different compound with different characteristics. The 2 compounds are called isomers. The molecular formula of each is the same, C4H10. One reason for these alternate structures lies in the fact that the 4 hybridized orbitals extend in different directions in the carbon atom. When 2 or 3 carbon atoms bond together, there's only one possible structural arrangement. But when 4 or more are bonded, then variations become possible. Carbon atoms can be added to the ends of the chain, or they can form a branch off the central part of the chain. So, isomers can be caused by variations in arrangement of atoms or variations in the positions of the multiple bonds. This is another reason that bonding characteristics account for the large number of carbon compounds. The chemical behavior of carbon compounds is influenced by another factor. A reactive group is a combination of atoms within a molecule that gives it a distinctive chemical behavior. For instance, in this molecule, these two atoms, oxygen and hydrogen, form a reactive group, an OH or hydroxyl group. The oxygen atom can form covalent bonds with the carbon atom and is often part of reactive groups. Carbon compounds containing the OH group are called alcohols. Compounds with the same reactive groups have similar chemical properties. These are models of molecules of alcohols. The carbon-hydrogen-oxygen reactive group is common in carbon compounds called the aldehydes. These compounds all have similar properties too. And this is the reactive group in the carboxylic acids. A few reactive groups contain nitrogen atoms, which also form covalent bonds with carbon atoms. These reactive groups are characteristic of amino acids, compounds which form the basis for proteins. Proteins are the chief building blocks of protoplasm, the essential living substance of which all cells of animals and plants are made. The role of carbon in living things gave scientists an important research tool. What is this tool? The atomic weight of carbon is a little over 12, based on an average relative mass of its 3 isotopes: carbon-12, carbon-13, and carbon-14. Carbon-12 is the common form. In the nucleus of a carbon-12 atom are 6 protons and 6 neutrons. The nucleus of the carbon-13 atom contains 6 protons and 7 neutrons. Carbon-13 is rare, but stable. However, the carbon-14 nucleus, with its 6 protons and 8 neutrons, is unstable and undergoes radioactive decay with a half-life of 5,580 years. This isotope is formed when nitrogen atoms are bombarded by neutrons produced by cosmic rays in the atmosphere. The nitrogen nucleus disintegrates, giving off a proton and becoming a nucleus of carbon-14. Carbon dioxide in the atmosphere contains mainly carbon-12 atoms and a few of carbon-13. A very small amount of carbon-14 is also present in carbon dioxide. Living plants absorb carbon dioxide as part of their food-making process of photosynthesis. As long as the plant is alive and growing, the ratio of carbon-14 to carbon-12 atoms will be approximately the same in the plant as it is in the atmosphere. But when the plant dies, ending its intake of carbon dioxide, the ratio between the 2 isotopes changes as the carbon-14 atoms decay but are not replenished. A comparison between this ratio in a dead plant and the unchanging ratio in the atmosphere gives an indication of how long the plant or the animal that ate the plant has been dead. This is the basis of the carbon dating technique that is used to determine the age of archaeological discoveries. So, for example, suppose we want to find the age of a piece of papyrus on which an ancient manuscript was written. Papyrus is a plant material. A fragment of the material is burned. When the papyrus is burned, its carbon is converted to carbon dioxide. An alternate method of carbon dating converts the material to liquid benzene. Then, the ratio of carbon-14 to carbon-12 in the converted material is measured in a radiation counter and its probable age determined. The discovery of radioactive carbon and its applications has added a new facet to the importance of carbon and its compounds.